Welcome back, everybody. This is our third session in JEE mains previous year questions for chapter Ray Optics and Optical Instrument. Before this video, we have made two videos in this series, and all of those videos are available on our YouTube channel's playlist section. We have also started similar series for NEET previous years. So if some of your friends are preparing for NEET, then you can guide them through those videos. And if you find these videos helpful or useful, then do press the like button, share it as much as possible, and subscribe to our channel. Also, if you like to support us financially, you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. With this, let's start today's video. In the previous one, we covered up to around 20. So that was the last one. Now let's start with the fresh. So here what we have in a figure, optical fiber of length 2 meter long has a diameter of 20 micrometer. If a ray of light incident at one of the fiber at angle theta 1 is equal to 40 degree, the number of reflection it makes before entering from the one end to the exiting to the other end. So first of all, let us see at this point what we can do. We can apply Snell's law at this point. So we can write that 1 into sine of 40 should equal to the refractive index, that is 1.31 here, and into sine of theta 2. Now sine 40 is already given to us 0.64, so 0.64 by 1.31 is equal to sine theta 2, and this will be approximately equal to half. So we can assume that sine of theta 2 is equal to half, and theta 2 is going to be 30 degrees. Now we have this value. Now in one reflection, here we at this point we are getting total internal reflection. So in one reflection, it is traveling this distance. Suppose that distance is d, and we know the diameter here, that this suppose this point is a, this is o, this is b. We know the value of diameter, or in short, we know the value of ab. Ab is here 20 micrometer. So from this triangle we can find the value of ob. We can write that AB by OB is equal to tangent of theta 2, means tangent of 30. And from this OB or D will be AB, that is 20 into 10 raised to power minus 6 divided by tangent 30, that is going to give us 1 by root 3. So this will be basically 20 root 3 and 10 raised to power minus 6, or we can say 20 root 3 micrometers. So that is the distance. Now in one TIR we are covering distance d, and we have to cover total 2 meters. So we can say that suppose if there are n number of reflection or n number of TIRs, into distance d should be equal to 2, and from this n is equal to 2 by d. So 2 by 20 root 3 into 10 raised to power 6 this will be, and when we solve this we will get 57735, and that nearly matches to, this is 5 here, basically it matches with the option D here. So option D will be the right one here. Let us move to the next one. A light wave is incident normally on a glass slab of refractive index 1.5 if 4% of the light gets reflected and the amplitude of the electric field of the incident wave is 30 volt per meter, then the amplitude of electric field for the wave propagating in the glass medium will be. Now to solve this one, suppose we have a glass slab here. Okay, so let us pick this one. So suppose this is glass slab, and here we have incident wave. Suppose this is our incident wave and it is incidenting normally. So suppose this is incident wave, and here we have transmitted wave also. So suppose this is transmitted wave. So For both, we know the intensity ratios, that here, uh, if I is the original one, then we can say refracted wave, or inside here, suppose that is IA, so that will be 96 by 100 times of I, and from this we can write that IA by I will be 96 by 100. Now IA is the wave inside the glass slab, and I is the original wave, or intensity of the original wave. Now for intensity, we have a relation that from EM theory we have no intensity is half epsilon naught E square into C. This will be in vacuum or in air. And for IA, we will have relation as it is entered in a medium with some dielectric constant, suppose that is K. So that will be half K epsilon naught electric field will be suppose EA square into value of velocity of EM wave in that medium. So from this, if we divide both of these two, so we will get IA by I, half epsilon naught will get cancelled, and what we will get? We will get K times EA square into V divided by E square into C. Now, uh, let us find out first ratio for V and C. Now we know that C is equal to under root mu naught epsilon naught, and inside the medium velocity will be V, and that will be equal to K times mu naught times epsilon naught, assuming that material is non-magnetic. So we are not considering mu r here. So if this can be written as like this, under root K into C, and from this C will be on the upper side, and from this V by C will be equal to under root 1 by K. Now substitute it here. So what we will get? We will get K into K divided by under root K into EA square divided by E, and this whole term is equal to 96 by, and this is square also, 96 by 100. So basically we have under root K into EA square by E square is equal to 96 by 100. And we also know that C by V is equal to refractive index, and C by V is here, that will be under root K. So basically under root K will be equal to the refractive index. So this relation will be converted into that mu into EA square by E square is equal to 96 by 100. Now we have been given value of mu, that is 1.5 or 3 by 2. So 3 by 2 EA square by E square is 96 by 100. This will go on 50. This will go on 32. So from this, EA will be equal to E times under root 32 by 50. Now value of E is given to us, that is given to us 30. So this is 30, and what we do inside, we will multiply by 2 and divide by 2. Now 32 into 2, that will be 64, and divided by 50 into 2, that is 100. So this will 30 into 8 by 10, and this will give us 24. So that is the value of EA, and it matches with here option C. Now let us move ahead for the next one. Let the refractive index of a denser medium with respect to a rarer medium be n12, and critical angle will be theta c at the angle of incident A. When light is traveling from denser medium to rarer medium, the part of light reflected and the rest is refracted. The angle between the reflected and refracted rays is 90 degree. Angle A is given by. So we have to find out angle of incidence here. So again, let us consider a slab here. Suppose this is slab, and we have a light falling on it. Suppose this is our incident light, and after refraction it moves like this, and there will be normal. So suppose this is our normal. Now it is mentioned that angle of incidence is A. So here this angle will be A. Now we can assume that as there is reflected light also, so let me plot it that also. Suppose this is the reflected light here. Now law of reflection states uh, that this angle will also be A, and as mentioned here that here, yes, the angle between the reflected and refracted light is 90 degree. So this angle is 90 degree. So this angle will be equal to 90 minus A, because total angle is 180, out of which this is 90, so remaining, and this is A, so remaining will be 90 minus A. Now at this point we can apply Snell's law, that here refractive index is N12, and assuming air of refractive index 1, so we will have N12 sine of A is equal to 1 into sine of 90 minus A. So from this N12 is equal to sine 90 minus theta is cos theta, so cos of A by sine of A, and that will be equal to cot of A. Now we have to find out critical angle. So for critical angle we know that sine of theta c for a critical angle is equal to 1 by refractive index or 1 by N2, and here 1 by N2 will be equal to 1 by cot, and that will be tangent of A. And if we adjust it slightly, then we can write that theta c will be equal to sine inverse tangent of A. Or okay, so we have to find value of A. So value of A will be tangent inverse sine of theta c. So that will match with option D here. Let us move ahead. A driver looking up through a water sees an outside world contained in a circular horizon. The refractive index of the water is 4 by 3, and driver's eyes are 15 meter below the surface of the water. The radius of the circle will be. So when driver will be seeing, then he will be seeing through a conical shape like this. Let me plot it and rotate it. Yes, here it is. Wait a minute. I need to rotate it. Yes. So what is happening here? Suppose here is the driver, and this whole system is in some material of refractive index. Let me change the color. Yes. So this whole is in some material of refractive index. That refractive index is 4 by 3. And let me slightly over. It will be like this. Yes. So here refractive index is 4 by 3 and is 4 by 3. So what is happening here? That light from this point is going like this, and after certain point here at from center at this distance, it is getting totally internally reflected. So driver can't see beyond this point on the both sides, and if in case of 3D, so he cannot see beyond these points because light will be traveling like this. So he can only see in a conical shape, and we have to find out this radius. So for that, what we can do, if we draw a normal here, then this will be the critical angle or theta c, and that will be again equal to this angle, that theta c. So theta c will be equal to sine inverse 1 by mu, or that will be 3 by 4, and from this sine of theta c we have equal to 3 by 4. Now this depth is given 15 centimeter, means this distance is 15 centimeter here. So from this what we can find out? We can find out tangent of theta c. If sine of theta c using triangle, that suppose this is theta c, and this will be 3, this will be 4, so this will be 16 minus 9 or under root 7. So tangent of theta c here will be 3 by root 7. And in this triangle, here in this triangle, tangent of theta c will be, suppose this is radius and this is depth. So tangent of theta c will be equal to radius by depth, that is d. Now tangent of theta c here is 3 by root 7 is equal to r by depth, that is 15. So r will be 45 by root 7 or 15 into 3 by root 7, that is option D here. Let us move ahead. A printed page is presented by a glass or pressed by a glass of water. The refractive index of the glass and the water are 1.5 and 1.33 respectively. If the thickness of the bottom of the glass is 1 meter and depth of the water is 5 centimeter, how much the page will be appear to be shifted if viewed from the top? So suppose this is our glass and there is some liquid inside it, and on the base of it, its base is thicker, made of glass, and it is going to have some thickness, that is 1 centimeter. This thickness is 1 centimeter, and here thickness of water or depth of the water is 5 centimeter. So what we have to take make an assumption here that we are dealing with small angles. So in that scenario, we have apparent depth or d apparent is equal to d actual. Here for water this will be 5 divided by the refractive index of the water, and that is 1.33, plus for the glass that is 1 actual depth, and divided by the refractive index of the glass, that is 1.5. So in total this will give us 4.43 centimeter, and the shift will be, or we can say shift, that will be total distance, total actual distance or actual depth, that is 5 plus 1 6 minus 4.43, and this will give us 1.57 centimeter, and the nearest one here is, that will be option C. So let us move ahead. A light ray falls on a square glass slab as shown in the diagram. The index of refraction of the glass, if total internal reflection occurs at the vertical face, is equal to. So we have to find that what will be the value of refractive index here, so that at this point we are having total internal reflection. So first we will draw a normal here so that we can find this angle. Now assume this angle is phi. So this angle will be 90 minus phi. Now at this point we can apply Snell's law, that 1 into sine of 45 is equal to refractive index of the glass here, that is given to be, it is not mentioned here. Oh sorry, we have to calculate the refractive index, so we take it as mu into sine of phi. Now sine of 45 will be 1 by root 2. So from this 1 by root 2 is equal to mu times sine phi. Now at this point there is total internal reflection happening. So if there is total internal reflection happening, then we can write that sine of 90 minus phi should be equal to 1 by mu. This is a condition for total internal reflection, condition for the critical angle. And from this we have cos of phi is equal to 1 by mu. Now we can draw a triangle here, that if this angle is phi, then cos phi will be like this. This will be 1 and this will be mu, and then this side will be equal to mu square minus 1, and from this triangle sine of phi will be equal to under root mu square minus 1 divided by mu. We can substitute it here. So 1 by root 2 will be equal to mu get cancelled, and this will be under root mu square minus 1. Squaring both sides, we will get half is equal to mu square minus 1, and from this mu square will be 3 by 2, and mu will be under root 3 by 2. That is option D here. Let us move ahead. Light is incident from a medium into air at two possible angles, 20 and 40 degree. In a medium, light travels 3 centimeter in 2 nanoseconds. The ray will. So we have to find that whether it will suffer a total internal reflection or not. So we have the distance traveled in the time. So velocity of light will be 3 into 10 raised to power minus 2. That is distance divided by 0.2 nanoseconds. So that will be 2 into 10 raised to power minus 10. And this will give us 1.5 into 10 raised to power 8 meter per second. That is velocity. And then the refractive index, mu will be 3 into 10 raised to power 8 divided by 1.5 into 10 raised to power 8. That will be equal to 2. So critical angle will be here, sine of theta c will be equal to 1 by 2, and from this theta c will be equal to 30 degrees. So if angle of incidence is greater than 30 degree, then there will be total internal reflection. So light A, for which total angle of incidence is 20 degree, will not suffer, and for B it will suffer total internal reflection. So and when total internal reflection happens, let me draw it, that suppose this is our medium and light strikes at this point, and if there is total internal reflection happening, means whole light is reflected into the same medium. Means here transmission or here reflection is 100%. Reflection is 100% and transmission is 0%. So let us see option A, that suffer total internal reflection in both cases. So in both cases there is no TIR, only in case B. Suffer, yes, in B. Have partial reflection and partial transmission in case of B. So that is also wrong, because in case of B we have total reflection and have 100% transmission in case A. Now when light is going to strike, even there is no TIR, suppose this is our medium, sorry, and this is the point at which light is incidenting. So when light strikes here, only in case of TIR it is 100% reflected. But if light is getting transmitted, so some part is getting transmitted and some part is also getting reflected due to boundary change. So there will be no 100% transmission. So option D is also wrong here. So only option B is the right one. Now let us move ahead. Let xz be the boundary between two transparent medium. Medium 1 is z greater than 0 and refractive index of root 2, and medium 2 has z less than 0 and refractive index root 3. A ray of light in medium given by the vector this is incident in the plane of separation. The angle of refraction in the medium 2 is. So here what we have, suppose this is the boundary. This is region z less than 0 and this is region z greater than 0. So for greater than 0 we have refractive index root 2, and for less than 0 we have refractive index root 3. So light is coming from the denser medium to the rarer medium, so TIR can also happen here. Now coming to the light, that light is given by this vector. So A is equal to 6 root 3 I plus 8 root 3 J and minus 10 of K. So first of all, what we have to do, we have to find out its angle of incidence. Now, as we know that here upper region is z less than 0 and lower region is z greater than 0, so this normal is parallel to z axis. This normal is parallel to z axis, and suppose this is the incident light here. This is the incident line. So we have to first calculate theta, and then we can use Snell's law of refraction to find this angle phi. Now, to do this, to find the theta, what we need to do first, we need to convert this light into a unit vector. Only then we can do angle calculations. So here unit vector will be 6 root 3 I plus 8 root 3 j minus 10 of k divided by the magnitude. So that will be 36 into 3, that will be 108 plus 64 into 3, that will be 192, I think, yes, and into plus 10 square, that is 100. So basically this will be 6 root 3 I plus 8 root 3 j minus of 10k divided by, this will be 300 plus 100 400, so divided by 20. So this is the unit vector of the direction of light, and as it is incident here and we have to find angle with the z axis, so what we do, we will do a dot product with the k. So a dot k will be equal to this will give us 0, so this will give us minus of half. Now when we are doing a dot k, so let me show you that how when we take normal dot products. So suppose this is vector A, this is vector B, and this is angle theta. So when we are taking dot products A dot B, then what we are getting? We are getting A dot B cos of theta. So angle between them is what we are getting. Now in case of here, both of the vectors are going outside, but here light is getting incident. So light is coming towards the this axis. Here our z vector is like this. Let me draw it. Here our z vector is like this, and why it is like this? Because uh, upper part is here, upper part is negative and lower part is positive, so it should go from the negative to the positive side, so like this. Now suppose this is some x or y axis, we don't know which is it in, either it can be x or y, but we know that it is z axis. Now here light is coming like this, light is coming like this, and it is going further. Now we are ignoring refraction here, so which angle we have to find out? We have to find out this angle theta. But at this point when we are taking theta, so here either both of the axes should be going outside, or both of the axis both of the direction should be the same, either coming or either going outside. At this point z is going downward, and here it is going like this, and here both are going downward also. So the angle which we will be taking here, it will be not theta in the dot product, it will be this one, that will be pi minus theta in the dot product. So now take this side, solve this side. Now magnitude of a unit vector will be 1 dot magnitude of k will be 1 into cos of pi minus theta will be equal to minus of half. And if we solve this one, cos of minus theta is negative, so it will be minus cos theta is equal to minus of half, and from this theta will be equal to 60 degree. So angle of incidence here is 60 degree. Now we can apply law of refraction here, Snell's law basically. So what we will get? We will get root 2 sine of 60. Oh sorry, wait a minute, let me check that light a slight correction here, that we have to reverse the axis. Why? Because light is incident in the medium 1, and medium 1 is in z greater than 0. So this side is z greater than 0 and this side is z less than 0. And for greater than 0 we have refractive index root 2, and here we have refractive index root 3. So this will be root 2 into sine 60 and is equal to root 3 times sine of phi. So from this, when we solve for the phi, what we will get? We will get phi is equal to 45 degree. So here it matches with the option A. So option A is the right one here. Hopefully you understood whatever we have covered here. And again, if you have any doubts or suggestions, you can put them in comment section. We will try to resolve them. And if you like this video, then do share it and subscribe to our channel. Also, if you like to donate us something, you can scan this QR code. With this, again, thanks for watching and we will meet in next video.